All right, for a quick review of what we learned the other day in class about expected value, standard deviation and variance of random variables. Remember what we talk about the expected value, E of x, is the sum of all outcomes times the probability of each outcome. When we talk about variance, we say that variance of a variable is the sum of each outcome's deviation from the mean squared times that probability. Remember, the mean is the same thing as whatever we get for our expected value. The expected value can be seen as the mean of the set. So take the deviation of each outcome from the mean, square it, times by the probabilities. And we said that standard deviation is the same as square root of the variance. Now, what we started to look at in your yellow note sheet, where we were talking about that dice game, is we started to see that when you double the point values, all it does is it doubles the expected value. And so actually, here's what our rule is going to be, is that let's say you double the value of that dice game. The expected value is doubling the actual points. That's what the outcome here is. X is representing the points in the game. If we double that, that's the same as saying 2 times whatever the expected value was. So we saw on our sheet that the original expected value was worth 10. So if we double all the points in the game, that's the same as saying that it's worth 20 now in the new game. When you double the value, your variance actually does more than double. Your variance will, in fact, put the double on the outside, but it becomes squared times the variance. And again, think about our formula. The formula has this squared up here, so it makes sense that we would not just double, but square that double. So for example, if the variance of something was worth 8, we would say that doubling the variance would actually be 2 squared times 8, which is 4 times 8, which is 32. So these two things here, this one for doubling expected value, and this one for doubling variance. Now, let's say you're not multiplying. Let's say that instead you're adding points. So you're playing the dice game, but this time you decide to give every outcome an additional 5 points. This would go ahead and do the expected value plus 5. So again, if our expected value was 10, then to have all points plus 5 would go ahead and say 10 plus 5 would have 15. And the same would be true if we wanted to subtract 5 points. So instead of adding 5 points, we decide to subtract 5 points. It's whatever the original expected value was with that change in place. Okay, so this guy would be our formula for adding or subtracting on expected value. When it comes to variance, however, if you are going to add or subtract however many points you want, as long as this is a constant for everything, it's actually not going to change the variance at all. We talked about this back in previous chapters when we said, hey, let's give everyone a Christmas bonus, and everyone gets a $50 Christmas bonus. The CEO gets a Christmas bonus, and the lowly hour worker gets a Christmas bonus. It's the same Christmas bonus, and so we said the difference between the workers is not going to change, and that's what variation measures. So notice that variation does not change when you add or subtract a constant. So that's when you're doing something to all the points within a set. Let's talk about combining two events. So when you're combining two events, this is a little different. This could be like when you play the game twice, for example. Play the same game twice, which we started to look at but didn't quite finish in your yellow note sheet. Or this could be when you play 2 games combined. So you play a dice game, but you also play a card game. Now, as long as they are independent events, and this is important, remember the outcome of one game does not affect the outcome of another game. So independent events, independent games, then these rules hold. This is where you get expected value. This would be the subscript if I played the same game twice, because the game is X, and this is the first time I play it, this is the second time I play it. This would be the same as the expected value of X1 plus the expected value of X2. You would simply add the expected values. If I was going to play two games, perhaps one is the card game and one is the dice game, then I would take the expected value of the card game plus the expected value of the dice game and add those. This is also true for subtracting between games. So I'm not just adding the points of two games. Perhaps I want to know the difference between my score and a friend's score to see who scored higher. So for plus or minuses, these hold. And really it's the same rule. I'm just going to highlight one of them, but the notation would just be this is the same game twice. These are actually two separate games, but same rule. For variance, it gets a little trickier. Let's say you're going to play the same game twice. It'd be the variance of the first game plus the variance of the second game. Notice that over here I could put the plus minus. Maybe I want to add or subtract from two games. However, my variance still is only a plus. So it looks very similar to this top equation, except that whether I add or subtract in here, this is always a plus right in here. And of course, the same would be true if I said I'm going to do the variance of a card game plus or minus a dice game. It's the variance of the card game plus and only plus the variance of the dice game. You might be saying, why is it only a plus? Why doesn't it change? That's something we can talk about a little bit more in class when I get back, but to give you a basic idea, I want you to think about you have a jar or a pitcher of lemonade, and in that pitcher of lemonade, you have a glass, and you decide to pour some of the lemonade into the glass. However, you're not quite sure how much lemonade you had to start with. You were uncertain about it. So when you subtracted lemonade from the pitcher and put it into the glass, and again, you're not really quite sure how much the glass holds either, you have the uncertainty of the pitcher and the uncertainty of the glass. And even though you are subtracting the lemonade, which would be subtracting one value of a game from another game, you have double the variance, or two sets of variance. You have the variance of the pitcher and the variance of the glass. We'll talk more about that, like I said, when I get back. But for your formulas today, just know that variances always add. You never subtract variances from one another. So even if it says take the difference of points, you subtract the variances. And the second big idea, which we talked about on your yellow sheet, was the Pythagorean theorem of statistics. So we said that the hypotenuse of a triangle is not just the addition of the sides. We said you always had to square these to make this work. So remember that you do not add standard deviations, and again, you wouldn't subtract either from what we just said here. You always add variances. You do not add standard deviations. You add variances. So if they're giving you standard deviations, you need to convert those to a variance first before you do any addition. So now that we reviewed our formulas a little bit, let's go ahead and look at some examples before you try your homework for tonight. First one we're going to look at here is just to remind ourselves how to find expected value and standard deviation of the random variable. So again, expected value, or the mu, the expected value of this variable x is the sum of all outcomes time each outcome's probability. So I have the outcome of 0 times the probability of 0.2 plus the outcome of 1 times the probability of 0.4 plus the outcome of 2 times the probability of 4. And so this one, would come out to be 1.2. And then if I want to find the standard deviation, I need to first find the variance of x, which means I need the sum of each outcome minus the mu squared times the probability of x. So this will be 0 minus 1.2 squared times the probability of 0.2 plus 1 minus 1.2 squared times probability of 0.4 and plus 2 minus 1.2 squared times the probability of 4. And then whatever answer we end up getting here, that's the variance. So to get standard deviation, you want to make sure that you square root that answer. So square root this would give you standard deviation. And now let's take a look at what the new rules are that we learned for today for combining variables. So here it tells us that we have independent variables, so x and y are independent of each other, gives us the means and standard deviations for each one, so they've already found the expected value, or the mu, and the standard deviation. And we want to do the combinations here. So this first one here, part A, this is the variable of x subtracting 20 points from, let's assume that these are points for right now. So we'll say e of x minus 20 is the same as e of x minus 20. And e of x was the 80. So we have 80 minus 20, 60. And then standard deviation, we have to work with variance first, remember. So variance of x minus 20 is saying that everyone had the exact same points happen to them. So it's just variance of x, does not change. And if there was no change in the variance, there's not going to be a change in the standard deviation either. So we're going to say that standard deviation is also 12. Part B. Part B is we're multiplying something times y here. So the expected value of 0.5 times y means that we take 0.5 times the expected value of y. So 0.5 times 12, which would be 6. And again, let's do variance 0.5 times y. This is where we square the 0.5 times variance of y. So this is 0.25. Now variance of y is not given. What we were given was the standard deviation of y. So standard deviation of y is 3. So that would mean that the variance of y is equal to 9. So 9/4, which is 2.25. And then to get it back to standard deviation, so therefore standard deviation of y is the square root of 2.25. I do not know what that is without my calculator, but there you are. Part C is the combination of x and y. So expected value of x plus y is the same as the expected values of each separately. So this would be 80 plus 12, or 92. And again, we have to do variations here. So let's just go ahead and make a variation column since we're having to use these more frequently. This would be 144 would be the variance for x, and 9 for y. There we go. So variation of x plus y is the variation of x plus the variation of y. So variation of x we said was 144 plus 9, which would give us 153. So to find the standard deviation of x plus y would be the square root of 153, 12 point something in there. All right. And D, now D is the subtraction of these, so the expected value of x minus y For expected values, remember you can subtract, so 80 minus 12 would give you 68. But we said variances always add. So actually, it would be the same process here, even though you're subtracting versus adding. So I'm not going to redo all that. I'm just going to say standard deviation is also this one for the subtraction there. And this one here is playing the same game twice, example. So we want the expected value of y1 minus y2, which means that we want expected value of y1 minus expected value of y2, and that would be 12 minus 12, which is 0. Makes sense. Same game, and we're subtracting the difference. Variance, though, means I actually still have to add my variances. So variance of y1 plus the variance of y2. And the variances were 9. So 9 plus 9 equals 18. Therefore, the standard deviation of that difference would be square root of 18 is what? 3 square root 2. So 4 something. 4 point something. That should give you a good idea how to do your second homework problem. And then this last one is really the same idea as what we just did, but with a context application. In this last example that we have here, we are at a grocery store, and the grocer believes that in 1 dozen eggs, the mean number of broken eggs is 0.6, so that is our mu, or our expected value, and the standard deviation is 0.5 eggs. We buy 3 dozen eggs without opening them, and so we want to know how many broken eggs do we expect, etc. This first thing here, how many broken eggs do I expect? This is asking about my expected value. This is like saying I got 1 carton of eggs, plus I got a second carton of eggs, plus I got a third carton of eggs. They're all the same variable, eggs. It's not like I did eggs and squashed grapefruit and rotten potatoes. It's all eggs, eggs, eggs. So it's all this guy right here. But it's a first case of eggs, a second case of eggs, a third case of eggs. A common mistake is to want to say, oh, I'm just getting 3 times x's, right? That would be saying, no, 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 that the probability of broken eggs is 3 times higher. So that's a common mistake to want to say it's 3 times, but what you're saying is you had 1 event, a second event, and a third event, or 1, 2, and 3 cartons. So not this one, but separate ones here. So for our expected value, we will say it is 0.6 plus 0.6 plus 0.6, which is 1.8 broken eggs are expected in 3 cartons. Making sure that we're having x1 plus x2 plus x3, 3 distinct cases, becomes important when they ask us about standard deviation. Because for standard deviation, we have to go back to variance, and in variance, it's important that we say x1 plus x2 plus x3, and not if we had done this incorrect way. If we were talking about variance of 3x, we know that that's the same as doing this guy, and that would connect with this wrong one up there. But for this case, when we're talking about adding or subtracting variances with each other, we will go ahead and still say that we are adding discrete cases. So variance was, let's see, standard deviation was 0.5. So variance would be that squared. 0.5 squared plus 0.5 of that squared for the second carton, and for the third carton again. Squaring it because those are variances of this, that Pythagorean theorem of statistics. 0.25 plus 0.25 plus 0.25. So we have 0.75 broken eggs would be the variance. So I need standard deviation of this. Standard deviation of x1 plus x2 plus x3 would be the square root of 0.75 broken eggs, whatever that decimal answer is. And then last part here, what assumptions did we have to make about the eggs in order to answer this question? We assumed that the cartons, or each event, were independent of each other. Meaning, if I open one carton and find a broken egg, that says nothing about how many broken eggs are in the next carton. So that's what we assumed, independent events. 3 homework problems for you guys to try tonight from chapter 16. Similar to what we just saw, okay, so practicing those rules, and then an application problem. We'll discuss questions on these and any other questions you have on chapter 15 homework. If you did not finish that already, please do. When are your turn?